Helps if everyone can hear me. Great. Okay. Hi, everybody. I'm Kendall Sullivan. I'm a postdoc at UC Santa Cruz, and I'm going to change the tone a little bit. And instead of talking about M dwarfs or brown dwarfs, I'm going to be talking about the stellar systems portion of this session, where we've been using planets in binary star systems to help understand planet formation. So because this is a crowd of stellar astronomers and not an exoplanet conference, I just wanted to start with the contractually obligated plot of planetary mass versus orbital period of planets that we've discovered using a variety of different detection techniques. And I'm not going to dwell on this because many of you have probably seen this before, but I just wanted to emphasize that we found a lot of planets. And if you look at the green color coding on this plot, that's the planets that have been found using the transit method, where you find dips in the stellar light because of the planet passing in front of the star. One of the things you might notice from this plot is that exoplanet systems are extremely diverse. They exist at a wide range of masses and radii and orbital separations. And as we've accumulated this diverse sample of exoplanets, one of the things that we found is that there are some really interesting features. So this plot is showing the relative number of planets as a function of planet radius for small planets. And the lines are just showing different studies, which all find the same thing, which is that the distribution of small planets is not unimodal, where we see, or flat, or anything like that. Instead, what we see is bimodal distribution of planet radii. So at the high radius end, from about 2 to 4 Earth radii, what we see is the sub-Neptune population, which are probably some combination of worlds with high water mass fractions and of rocky worlds with gaseous envelopes. What we think happens is that some of these original sub-Neptunes, because we think most planets form with an atmosphere, actually undergo mass loss of some sort, and they form the super-Earth population, which is at small radii. And because of scale height arguments and things like that, you can actually start to suggest that that naturally forms your radius gap. So if you have an atmospheric mass loss that causes this bimodal distribution, we might start to ask what early conditions of planet formation dictate these properties that we observe of the mature planet population. And it's really difficult to find young planets. So the way that I've been trying to approach this is using binary star systems. So we've already seen this plot a couple of times today, even. This is showing the multiplicity fraction as a function of primary star mass. And what we can see is that across all spectral types, binary stars are common. So primary star mass is at the bottom for the observer's spectral type is at the top. And what you can see, the systems that I focus mostly on are not the coolest stars, but instead the FGK stars, which have multiplicity fractions of about 50%. So this is a problem for a lot of you, and I'm sorry, but for me, this is really exciting because I like binary stars. And some of the things that we know about planet formation in binaries actually comes directly from observations of circumstellar disks. So for example, one of the things we know is that close binaries actually decrease disk lifetimes. This is a plot showing disk frequency in the Taurus star forming region, which has an age of 1 million years as a function or against binary separation. The blue band at the top is the single stars, and the red points are binaries at different separations. And you can see that the wide binaries have multiplicity or disk fractions that are similar to the single stars, but the close binaries have this steep decrease as a function of binary separation in the number of disks. So this suggests that the closer your binary is, the shorter lived or smaller your disk is. We also have found that close binaries decrease disk size, and this is by using millimeter flux as a proxy for the amount of the disk size or the disk mass. So this is showing millimeter flux against the projected separation of the binary, again, in the Taurus star forming region. The black dots on the right are the single stars, and then the color coding shows different separation regimes for the binaries. You can see that again, as the binary separation decreases, the millimeter flux also decreases, suggesting that you have less material in your disk to form planets. So this sort of naturally, to me, leads to this question of if binary stars impact planet formation enough to change the planet demographics that we observe. And there's already been some evidence of this for giant planets, as Clem and Daniela's work has started to show, but we're curious about the LOMAS, small planets. The challenge here is that planets and binaries are really difficult to find and characterize because of observational biases, which I'm totally going to gloss over. But just trust me that they're hard to find. But thankfully, some of them have snuck in to samples like the Kepler sample. So I came in at sort of the end of this survey, but there was this ongoing survey when I started grad school that Adam Krause was leading, using NERC2 on Keck to do adaptive optics imaging follow-up of binary candidate stars in the Kepler objects of interest sample. Then I came in and started taking optical low-resolution spectra of these known binary Kepler objects of interest hosts to recharacterize the stars and their planets to make sure that we had accurate planetary and stellar parameters that we could then use to do demographics. So we did this using the low resolution spectrograph on the Hobby Eberly telescope at McDonald Observatory. So using that sample that we assembled, we ended up with a sample of binaries that host small planets. We had 210 binary KOI host systems with projected separations less than 2 arcseconds and relatively low contrasts. And you can see that distribution on the right-hand plot of the contrast versus the separation. And you can see we're really sampling a lot of that parameter space. We ended up with a sample of about 280 planets with radii between 0.5 and 4 Earth radii in periods less than 100 days. So we're really excited about how big this sample was because it meant that we could do some really fun demographics. So the first thing we wanted to check is what is the planet radius distribution in binaries marginalized over the binary separation. And this plot is showing, you're going to see several versions of this plot with slightly different samples. This plot is showing the relative number of planets. So this is not occurrence rates. This is just observed planet distributions and showing the planetary radius. The black line is the single stars. And from Travis Berger's revision of the Kepler objects of interest properties. And the purple line is our full sample marginalized over binary separation. And you can see that already starting to maybe hint that there are some differences between the binary star population of planets and the single stars. But we could do more than this because we had our giant sample of 280 planets. So we know that the binary star properties for the disks are different as a function of binary separation. So perhaps the planet distribution is also different. So first, we plotted a separate distribution for the wide binaries. So these are binaries with separations greater than 300 AU. And statistically speaking, although you might be able to see some tantalizing differences if you chi-by-eye this between the two distributions, they're statistically indistinguishable. And the key thing to note here is that we see the same number of subneptunes, and we may see a radius gap in this distribution. So this is extremely similar to what we see in the single stars. In contrast, when you look at the close binary star distribution, we see some significant differences between the two populations. So first of all, there are very few subneptunes compared to the single star distribution, many fewer than we would expect. The other thing to note is that this distribution is unimodal. So instead of seeing a suppressed number of subneptunes, but a radius gap, and then the peak for the super Earths, instead what we see is a smooth decline from the super Earth peak, which is exactly where we would expect at 1.3 Earth radii, just down through the subneptune regime really smoothly. One thing to note here that I want to anticipate questions about in the Q&A and hopefully reduce those is that we assumed that all of these systems were around the primary star. And that's an assumption that I can back up based on observability arguments, but we were curious to see sort of what the most pessimistic outcome would be if half of our planets were around the secondary stars instead. And what we find is that for the close binary star distribution, the mode of the sample is basically the same. So this is reassuring that this result is robust to our assumptions. That said, I've been working with a student, Nathaniel Burns-Watson, who started with me as an REU last year and now is incoming to work with Adam at UT Austin, who's working on determining the planet host stars for some of the systems in this sample. So stay tuned for his paper, hopefully later this year. So I wanted to give a little bit of interpretation. So it looks like close binaries hosts fewer sub-Neptunes, and there's also this apparent lack of a radius gap. We're pretty sure this isn't an observational effect. So what we think is that multiplicity might be inhibiting the sub-Neptune formation in a variety of ways. So one possibility is that it's truncating the disks and reducing the number of icy solids that you can use to create sub-Neptunes. It's reducing the disk lifetime and thus the time scale for cores to accumulate the gas, and otherwise perturbing the disk from the secondary in ways that are complicating the sub-Neptune formation and survival. Yeah, and the paper was accepted on Monday and it was up on arXiv as of yesterday. So if you're interested in the details, there's a little QR code there. Yeah, so we found that planet formation in binary stars might be impacted by stellar multiplicity. And I want to end with a plea to the theorists to please help me figure out what's going on here. because I can make arguments based on vibes, but and physical intuition, but having some robust theory would be great. So thank you.
Also remind you to ask questions and to repeat the question for them.
Thank you, Fred Adams. Quick question. You showed for your case and also for bipolar cases that there's actually a peak of the rocky phase at. Can you comment on, is that a real peak? Is that a liquid mass? Or are you just missing the small things? That would help us do this a lot.
Yeah, I am definitely not an expert in the occurrence rate sensitivities, but sensitivity does definitely drop as you go to the smaller radii. So I think, I don't remember the exact plots for the occurrence rates, but I think there is an expectation that they will increase as you go to the smaller masses, but I'm not exactly sure what the shape of that distribution would be. So yeah, I'm not sure if that peak is correct or not, but I think it's probably at least partially a sensitivity effect. No. The sample is too small for that, unfortunately. So we only had about 100 planets in each of our bins of the greater than 300 AU and the less than 100 AU separations. So one of the things that I am really hoping for is some of the, we're looking at tests to try and expand this sample. And then I'm hoping that Plato will also provide a larger sample of transiting planets in binaries where we can get a really robust sample to do this kind of work. I'm just gonna let you do this.